All right, so today I'll be giving a presentation entitled A Theory-Driven Incremental Approach to Constructing Minds Using the LIDA Cognitive Architecture. In retrospect, I wish I'd chosen something a little more pithy for my title, something like, I don't know, Managing Complexity, but that doesn't quite work. I mean, what's the context? So maybe I should have chosen Managing Complexity in Cognitive Modeling. It's better, but still vague. What's the plan? I mean, you must be thinking, how will this guy bore us for 30 minutes? Okay, so I think I have it this time. Managing complexity in cognitive modeling by way of a bottom-up and incremental synthetic approach to understanding minds. Okay, there. Now you know precisely how I will bore you for the next 30 minutes. But wait, isn't this a symposium on cognitive architectures? What's this guy trying to pull here? Okay, here it is. I got it this time. Managing complexity in cognitive modeling by way of a bottom-up and incremental synthetic approach to understanding minds illustrated using the LIDA cognitive architecture. Maybe on second thought, probably should go back to the original title. Okay, so in the previous slide, I mentioned the word complexity multiple times. And I hinted at the fact that complexity is somehow important for the topic at hand. But I didn't explain what I meant by complexity or why it matters. Specifically, for the purpose of this talk, I'm interested in managing two different kinds of complexity. The first of these is the complexity that's inherent in the agent development process. The relevant issues here are, what's the best process for adding new features to an autonomous agent? How do we avoid over-engineering? How do we evaluate what we built? And how do we ensure that nothing gets broken as we add new features? I mean, these are standard software engineering concerns that are just exacerbated by these unique challenges presented by the cognitive modeling problem domain. The second is the complexity inherent in our cognitive architectures. I mean, in my opinion, cognitive architectures should strive to be capable of modeling all cognitive activities and processes, including perception, motivations, action selection, motor control, attention, learning, planning, metacognition, sense of body, self, mental simulation, and language. Or in Alan Newell's words, they should strive to be unified theories of cognition. Unfortunately, minds are complicated and modeling minds is hard. So it's not surprising that our cognitive architectures are also complicated. And managing this complexity so that the richness of our theories doesn't become a barrier to understanding them is a worthwhile pursuit. So for this presentation, exploring one approach for managing these sources of complexity is the topic of this presentation. In the mid to late 1980s and early 1990s, Stuart Wilson began developing and advocating for a methodology for studying artificial minds called the Animat Approach. The Animat Approach is a bottom-up and incremental synthetic methodology. It's a synthetic methodology because it advocates for understanding minds by building them. It's a bottom-up methodology because it begins with very simple agents that are situated in a part of very simple environments. And it's incremental because it gradually increases complexity in response to environmental complexity. The Animat Approach, at least as Stuart Wilson originally described it, use naturalistic virtual environments and species of artificial animals that he called animats, which were driven by biologically inspired survival-oriented needs. Wilson argued that modeling these intrinsic motivations is essential since they're likely the principal drivers of behavior and shape how agents perceive and conceive of their worlds. According to this approach, animat quality is judged solely on its ability to enact adaptive behaviors that allow it to survive and thrive within these environments and to satisfy their own needs. In other words, the Animat Approach uses a purely performance-based evaluation criterion. And presumably Wilson had hoped that his animats would eventually resemble some kind of a natural species, at least in terms of their overt behaviors, but there's no mechanism that's built into the animat methodology to enforce or even to encourage this. I'll return to this point later. Finally, the Animat Approach stresses the building and the study of complete systems rather than isolated subsystems that support adaptive behavior. The idea of focusing on complete systems was not new even in the 1980s. It goes back at least to 1973 with Alan Newell's arguments, and you can't play 20 questions with nature and win. Roddy Brooks, the creator of the subsumption architecture, later echoed this sentiment in the 1990s when he said, "We must incrementally build up the capabilities of intelligent systems, having complete systems at each step of the way, and thus automatically ensure that the pieces in their interfaces are valid." Ultimately, cognition is for the selection and execution of actions, so it stands to reason that in order to fully understand these specialized subsystems, one must study them within the context of an autonomous agential system, at least at some point. Return to the business of managing complexity. This diagram captures what I believe to be the essence of the Animat methodology as a software engineering process. First, we start with some new challenge, or if it's your initial challenge, it's just the first environment. And that those new challenges could be new environmental pressures or more sophisticated intrinsic motivations that are more difficult for the agent to satisfy. Given this new challenge, we update our environment and the needs of the agent to reflect this new problem specification. We then test the agent against this new challenge and verify that it fails to rise to the occasion. If it passes, then we're done. No need to update the agent's control structures. We move on to the next challenge. Note that agents with the ability to learn from their experiences may be able to deal with many new challenges without changing the code in any way. So this initial check is critical to avoid over-engineering. If the agent does fail to survive and thrive under these new conditions, we make the minimum necessary modifications to the agent's control structure that allows it to succeed. And by succeed, I mean both at this new challenge and all of the previous challenges. You can't forget the stuff that it previously did, because it needs to survive under those conditions as well. So assuming the agent was successful with all of that, we can then optimize our agent. We can reduce its design complexity or improve its performance, whatever it is, as long as it maintains that ability to survive and thrive in the environment. And so it goes. This process just continues. Note this process stresses gradual changes to an agent in its environment. It's never a wholesale replacement of either of those. It implies a maximal reuse of an agent's previous capabilities to allow minimal software changes at each step. And it results in a co-evolution between an agent and its environment. Now, it may have occurred to some of you that were looking at the previous diagram that it looks suspiciously like test-driven development. If you notice that, good for you. In my reckoning, when you remove the Animat Approach's overarching philosophy and boil it down to a development process, it's essentially identical to the software engineering practice of test-driven development. Okay, so earlier I mentioned that the classical Animat approach evaluates the quality of software agents based on their ability to cope with environmental challenges and satisfy their own needs. This performance-based criterion is useful because it lends itself to objective comparisons between different Animat designs. However, there's nothing in this approach that constrains the minds of these software agents to be similar to natural minds, for example, human-like minds. So the practitioners of the classical Animat approach are free to choose any mechanism mind that gets the job done. And this led me to wonder if this classical Animat approach could be used in conjunction with a cognitive theory that captures our current hypotheses about how natural minds work. So in other words, can we use a cognitive architecture to constrain Animat designs to the region of Animat design space that's consistent with that cognitive architecture? More importantly, can we use a cognitive architecture as a heuristic that'll help us to steer a trajectory through a progressive set of more sophisticated and generally intelligent animats that may eventually have human-like minds? So in the remainder of this presentation, I'll be exploring this possibility of applying an Animat style of agent development in conjunction with the cognitive architecture. Specifically, I'll be focusing on the LIDA cognitive architecture. I suspect this approach should work with other cognitive architectures, but I'm a LIDA guy, so I haven't gone through that exercise. I'll start first by going over some of the basic LIDA background so that you understand enough about LIDA to see, understand what follows. And then I'll try to demonstrate this theory-driven Animat approach in the context of a simple environment and agent. So LIDA stands for Learning Intelligent Decision Agent, which is a systems level, biologically inspired cognitive architecture. As part of its biological inspiration, LIDA implements and elaborates on numerous psychological and neuropsychological theories, such as the global workspace theory of consciousness, constructivist learning, a la Piaget and Gary Drescher, long-term working memory, System 1 and System 2 for Kahneman and Tversky, the two streams hypothesis, and perceptual signal systems from Lawrence Barcelow. LIDA is a hybrid cognitive architecture because it supports both symbolic and non-symbolic representations. LIDA has a commitment to grounded representations, and it contains both situated and embodied control processes. One final note about LIDA is that LIDA does not attempt to model brains, it models minds, where it defines minds as control structures for autonomous agents. Again, going sort of back to Newell. While what we know about brains has informed LIDA's design, LIDA does not attempt to model any neural dynamics or any brain anatomy directly. All of LIDA's cognitive activities and processes are conceptualized as occurring within or emerging as the result of a series of potentially overlapping cognitive cycles. These cognitive cycles correspond to the action and perception, or sometimes perception and action cycles, referred to by many psychologists and neuroscientists. LIDA's cognitive cycle begins with incoming sensory stimuli from an agent's environment and ends with the selection and execution of an appropriate action. Each cognitive cycle can be thought of as a cognitive atom, where higher level cognitive capabilities such as deliberation, reasoning, and planning may involve many cognitive cycles. LIDA's cognitive cycle is conceptually divided into three phases: a perception and understanding phase, an attention phase, and an action and learning phase. And I'll describe each of these phases in later slides. LIDA's cognitive cycle emerges from the collective activity of many short and long-term memory modules, as well as special purpose processors called codelets. Short-term memory modules such as sensory memory, which is depicted in this diagram in a tan-colored rectangular shape. And then there's the long-term memory modules such as perceptual associative memory, which are depicted as blue-colored rectangular shapes. And the conscious broadcast, which is depicted using orange-colored arrows. All the other arrows depict interactions that are unconscious interactions. Again, LIDA implements global workspace theory, the global workspace theory of consciousness. Most of LIDA's modules and processes operate asynchronously and in parallel, with the exception of its global workspace and the action selection modules, where processing is based on what we call triggers. So the first phase in LIDA's cognitive cycle is called the perception and understanding phase. During this phase, sensory stimuli from an agent's environment activate low-level feature detectors, for example, edge or color detectors, in LIDA's sensory memory module. These in turn may activate higher level representations in LIDA's perceptual associative memory, which is also known as PAM. And these representations typically correspond to objects, entities, events, and feelings, among other things. PAM representations that receive sufficient activation can be instantiated as percepts in LIDA's current situational model. And percepts, along with other pre-conscious representations in the current situational model, may cue long-term memory modules, other long-term memory modules, such as LIDA's declarative memory module, and result in the recall of representations into the current situational model. In parallel, structure building codelets can create or modify pre-conscious representations in the current situational model. For example, they may create simple associations between representations, such as causality links, or they may create more complex structures, such as those that correspond to mental simulations. The set of active, that is non-decayed representations in the current situational model can be interpreted as an agent's pre-conscious understanding or thoughts about its present situation. The next phase in LIDA's cognitive cycle is called the attention phase. So during this phase, attention codelets search for representations in the current situational model that are of interest to them based on their own concerns. Some of these concerns may be very general, for example, just based on the activation of those representations in the current situational model. While others can be extremely specific, for example, things like loudness, brightness, painfulness of an event, those things can be attended to by attention codelets. If an attention codelet finds preconscious representations matching their concerns, they'll bring that content to a coalition forming process. And this process creates a new coalition that includes both the attention codelet and the content that it promotes. These coalitions are then added to the global workspace, where they compete in a winner-take-all competition. The outcome of this competition is based solely on the coalition's activations. And then the content from that winning coalition is then globally broadcast to all of LIDA's modules. And this content is said to be conscious content. The final phase in LIDA's cognitive cycle is called the action and learning phase. Now, recall from the previous slide that the attention phase ends with a global broadcast, and that conscious content is then broadcast to all of LIDA's modules. The action and learning phase begins when LIDA's procedural memory module receives this content, which it then uses to activate its schemes. A scheme is a representation that corresponds to a learned correlation between a situational context, an action, and the expected results of that action. And this was inspired by the work of Gary Drescher, who was trying to implement Piaget's constructivism. Schemes receive activation when their context and their expected results are relevant. That is, to the relevant to the content in the conscious broadcast. Schemes that receive enough activation are instantiated and sent to LIDA's action selection module. We refer to these instantiated schemes as behaviors. Action selection chooses at most one behavior per cognitive cycle. It then sends the selected behavior to LIDA's sensory motor system for execution. The sensory motor system is composed of two modules, sensory motor memory and motor plan execution. Sensory motor memory is a long-term memory module that instantiates a motor plan based on the current selected behavior. And then motor plan execution will execute this motor plan and produce a sequence of motor commands that are sent to an agent's actuators for fulfillment. Once instantiated, a motor plan continues to execute motor commands through a process called online control. During this process, sensory content is sent directly from sensory memory to motor plan execution over the dorsal stream, allowing the selection of low-level motor commands by way of rapid processes that are directly coupled to the environment. And one thing that's important here is that this process of action execution is executing in parallel to other things that might be going on. So the agent may be planning and doing some other kinds of offline cognitive activity, all the while action execution can continue for the current motor plan. Finally, during this phase, LIDA's numerous learning mechanisms can also be invoked. Critically, learning in LIDA only occurs from conscious content, and this is a position inherited from the global workspace theory of consciousness. We refer to this as the conscious learning hypothesis. Okay, so in the remainder of this presentation, I'll attempt to demonstrate the theory-driven Animat approach in the context of an actual environment in a series of environmental challenges. My goal is not to provide a serious cognitive modeling exercise, but to show how this approach might proceed in practice. The same thought processes should be applicable for most agent development, even if the nature of those environmental challenges differ from the spirit of the classical Animat approach, meaning that it doesn't necessarily have to be an environment that is somehow naturalistic in composition. Okay, so we start here with a very simple environment that was loosely inspired by the European stag beetle. I can't tell you why exactly I chose this particular subject. I just think European stag beetles are cool, but don't laugh at me. For this first iteration of the theory-driven Animat process, my simple environment contains a single agent and randomly placed edibles. Edibles and agents emit smells. It's irrelevant that this actually, the agent has no visual sensors. It's all other types of sensors. Edibles also have tastes. These smells and tastes are encoded as 16-dimensional real number vectors that are basically kind of like a chemical signature for these things. And these vectors are additively combined, for smells anyway, into a single vector when the agent encounters multiple smells simultaneously. The concentric circles shown on the screen show the relative magnitude of the smells, which decrease as the distance between the agent and the smell emitters increases. So I'm going to play this video here. So this agent supports a number of different actions. It can rotate its body clockwise and counterclockwise. It can walk backwards. It can walk forwards. And it can also open and close its mandibles. It also has the ability to extend and retract a tongue-like appendage, which it can use to lap up liquid food, which I'll demonstrate later in this video. Finally, the agent can execute 2 or more actions in parallel. So it can, for example, walk forward and turn clockwise, open and close its mandibles all at the same time. And this is something that is missing, I think, in a lot of the environments that are used in machine learning research. These agents have a number of sensors, and I'm going to sort of just quickly go through this. They have 2 antennae that can separately receive smells, taste, and tactile information. They've got little hairs on their bodies, 15 of them, that respond to touch. And you can see that there's a visualization of these things up at the top, so you can see what the agent is currently picking up on. It also has, in this first environment, a health and a satiety sensor. Satiety gradually decreases over time. When it reaches 0, the agent begins to lose health and will eventually die. Eating food increases satiety. All right, let's see. And of course, you know, the greater the health and the satiety, the happier the agent is in some loose way. Okay, so for our first agent implementation, so again, our goal is to control the complexity by doing minimal leaps in complexity. So we want to use just a minimal set of LIDA modules and then add as we go along. So this minimal set, in this minimal set, sensory memory receives incoming sensory stimuli from the agent sensors, and the motor plan execution module oversees the execution of a single motor plan using a process of online control that I talked about earlier. This style of agent is purely reactive. This implementation of the sensor memory module doesn't contain any feature detectors yet. It merely forwards incoming sensory stimuli to the motor plan execution module to guide motor plan execution. This single motor plan is shown here. It's implemented in a subsumption architecture style, and it has 3 behavior modules: consume, seek, and wander. Wander is the lowest of these, and it will emit motor commands directing the agent to randomly walk around. Seek is the next level up, and it will emit motor commands that direct the agent towards food sources when the agent's intended to detect smells. And consume is the final layer, and it will emit motor commands that will consume a food source by first crushing it and then lapping up the liquid food with the agent's tongue. Finally, there's suppressed nodes that are shown in the diagram that indicate that higher layers can suppress the lower layers when those higher layers have motor commands to emit. Again, this agent is just purely reactive. Okay, so the next step up, so we're doing iteration 2 here. So in iteration 2, and I'm simplifying this process somewhat just to get through it. So we add an aggressor to the environment, and this aggressor will attack, and try to kill the agent. In this iteration, we also add pain receptors to the agent's body that receive a binary signal when the agent suffers an injury. And I'll just show this here. So this display on the left is actually the agent up at the top. The bottom one here is the aggressor. And all this is really showing you is just, the effect of the agent being attacked and then it dies. So in order to talk about this next iteration, I have to do a quick tour of motivations in LIDA. So at its most basic level, LIDA's primary drives are specified by a type of node in its perceptual associative memory module called a feeling node. Feeling nodes are different from LIDA standard nodes because they have what's called an associated valence sign. Valence sign is either positive or negative. Positive is liking, negative is disliking. And then the magnitude of activation that these nodes get is the degree of liking or disliking. And so we call the combination of valence sign and activation its effective valence. So for example, in this diagram, we have a feeling node that corresponds to the agent satiety, which is shown here. And when an agent satiety increases, a feature detector in sensory memory then would activate the satiety feeling node in perceptual associative memory, and it can be instantiated as a percept if it receives sufficient activation. This activation can then also propagate to other feeling nodes. The rest of the details here are not important, so I'm going to skip those. And I'm going to go to the next implementation, which is the iteration 2 implementation. Again, we're trying to just manage the complexity as much as possible. We're still, you saw the earlier diagrams of LIDA. We're just piece by piece adding what, might make sense to manage the complexity. So LIDA supports 4 different modes of action selection. One of them is alarms. And alarms, they are still purely unconscious. We haven't even added consciousness yet to this agent. The other modes of action selection that are supported by LIDA are volition or deliberative action selection, consciously mediated action selection, and automatizations.
Sean, you just have a couple minutes left.
Okay. Okay, yeah, I'll try to wrap it up then. So anyway, so this basic idea then, so one of the things I do want to point out is that, so if we were trying to, really minimize everything in terms of the number of changes, what we might have done is said, okay, well, let's change the motor plan that we used before and just do like subsumption architecture and just add another behavior module. But that violates some of the theory of LIDA. Its motor plans in LIDA should have different intentions, different purposes. And so LIDA as a theory enforces this other view of the way that things are doing and uses and alarms for this particular scenario or a natural way of modeling this stuff in LIDA. And I'll just kind of quickly go through that. And that was just the number of different things that needed to be added minimally for this. And then finally, there's another step over here. I'm actually going to skip over this iteration, but basically with this iteration, we're just looking at energy. So actions actually have an energy cost, which I think this is important to look at in agents overall. And so then this next implementation would cover that next step. And so we're gradually building up, LIDA. And then the next steps, the sky's the limit. It's based upon whatever the needs are of the environment. So quick conclusion. So the classic Animat approach was a bottom-up incremental synthetic approach. Animat methodology is very similar to test-driven development in practice. Theory-driven Animat approach is this idea of combining a classical Animat approach with a cognitive architecture. And it's possible this approach could help to manage the complexity in designing agents as well as in describing a cognitive architecture to somebody. And that's one of my big hopes. It's not clear to me yet whether this is actually going to be useful to do this. This was just a thought experiment in a lot of ways. But my hope is that this can be used to manage some of the complexity in a cognitive architecture. So with that, I am done.
Thank you very much. We just have time for one question right now. And that's the question from Pat Langley, if I can find it. Yes. Your diagram doesn't seem to include any mechanism for problem solving or heuristic search. Did I miss it, or do you think such mechanisms are necessary for intelligence? And I would add, sort of putting my own twist of the typical procedural control module that is found in many cognitive architectures.
Right. Yeah, that's a good question. And actually, it's somewhat deceptive, that diagram. This is something that I think a lot of people get confused about with LIDA, because ultimately, what you're talking about is, so these deliberative processes or problem-solving planning processes. LIDA models these as internal actions, and I've had some recent discussions about that. The diagram doesn't reflect this at all, that those exist, but it's in our very earliest literature. And internal actions would allow the modification of preconscious representations in the current situational model, and you can do this kind of problem-solving process. You can. I think that's essentially what you're talking about. That's how LIDA would implement it, is internal actions, whereas everything I've talked about so far, because of the simplicity of these agents, it's all external actions. So LIDA would support it, but I understand your confusion about it.